So the last speaker for the day is Ariel Smoler. Ariel, the floor is yours.
Hi everyone, thanks for having me. Sorry. Yeah, my name is Ariel. I co-founded and up until a few years ago was VP of Incident Response in Signia, which is a teammate cyber services company acquired by Classiq in 2018. Since then, I was strongly fascinated by quantum computers, and last couple of years, I was super fortunate to be part of the Classiq, truly amazing Classiq team as a quantum algorithms researcher. Today, I want to actually showcase an example of how quantum algorithms have the potential to actually enhance cybersecurity rather than just be a threat to it. Okay. Just to put things in context, so at a very high level, there are three key areas where quantum computers and cybersecurity interact. One is obviously the cryptographic threat, and a lot has been talked about it. I'm not going to go into it. I just want to mention one aspect that might be overlooked, and that's the opportunity to take the attacker's perspective on Shor's algorithm and actually play with it. And you can actually run it today on today's simulators and quantum computers. I think that's super practical. Number two are the quantum algorithms themselves. There's literally a zoo of quantum algorithms out there. Some of them show real promise and are relevant to cybersecurity. So if you want to get ahead in the curve within the cybersecurity domain, again, these are actually algorithms that you can run on today's noisy computers, and we'll go into that. And thirdly, securing quantum computers. That's also an interesting thing to explore. But today, I want to focus on bullet number 2, and I want to showcase a simple example on how the optimization QoOA algorithm can potentially enhance cybersecurity. So QoOA is a hybrid quantum classical algorithm. Basically, it's a special case of the VQE algorithm, which combines quantum circuits and classical optimization techniques to find the minimum energy of a system. What does that mean? It means that given that we can represent the total energy of a system as an Hamiltonian operator, which is a fancy word for a Hermitian matrix. Given that, we can initiate a quantum and classical hybrid loop to find the minimum energy of a system. And how do we do that? We prepare a quantum state using a parameterized quantum circuit, which we call an ansatz. We measure that circuit, we do some classic calculation, we send it to a classical optimizer, which then feeds back the parameters back to the parameterized quantum circuit, and then the algorithm hopefully converges to the minimum energy of the system. That's pretty cool, and actually depends obviously on representing the system, finding the Hamiltonian operator, 1, and 2, that the quantum circuit that is actually representing the search space actually has some meaning. It sounds great and actually works, but what's the relevance to cybersecurity? It sounds good for chemistry, it actually does work for chemistry. So apparently, graph optimization problems, they can be transformed into the Hamiltonian operator and solved with QoOA. So given a graph optimization problem, we can formalize it as a quadratic binary objective function, meaning we're looking for the binary variable x that will minimize this quadratic expression. Given that, we can mathematically transform it to a Hamiltonian operator, and now we can solve it with QoOA, and we'll show how to do that. Now that's getting pretty interesting because graph problems are actually pretty relevant to cybersecurity. Network topologies, routing, attack scenarios, investigating incidents across a timeline, these are all graph-related problems. And actually, graph databases are becoming increasingly significant in cybersecurity, AKA Wiz, our friends at JAM, These are all getting extremely popular and for a good reason. So if we can express a cybersecurity related problem as a graph optimization problem, we can now solve it with quantum computers using QAOA. Now, let's start with a super simple, straightforward example where the network topology is actually projected one-to-one as a straightforward graph. Bear in mind that there are more complex graph manipulation use cases that we're actually working with clients on, but we'll start with the simplest one. Sorry. Let's say we want to continuously monitor the network communication. And why do we want to do that? We want to search for indications of compromise. We want to make sure the network is healthy. We want to do some asset management. And we want to monitor our network while optimizing resources. Why do we want to optimize resources? So various examples. Let's take an IoT example. A certain IoT, for example, WSN networks, they're deployed in forests and mines and land borders and are typically battery powered. So energy consumption is actually a critical concern. Number two, power systems, nuclear plants. We've seen those are subjected to topology and state attacks, such as Stuxnet and so on. And apparently those can be effectively monitored and mitigated using an extremely expensive sensor, which is the phasor measurement units, the PMUs. Another reason we want to optimize our resources is to save money or or record more data. We just want to make sure we have we don't have any duplicates and we can store have our retention bigger. So in all these cases, we want to identify the smallest number or set of nodes in the network such that every link or communication link in the network is monitored by at least one of these nodes. And this is the min vertex cover. So in our toy example, let's say we have a simple network of 12 nodes. So the graph is pretty simple. Every vertex in the graph is a node in the network. Every edge in the graph is a communication link between the nodes. And we want to find the smallest set of nodes such that each edge in the graph is seen by at least one of these nodes. Apparently, this is an NP-hard complexity problem, and the QAOA has some promise with solving that. So let's actually do that. Okay, so in order to solve this problem with QAOA, and this is a really simple toy model, we first obviously need to find the Hamiltonian operator. Second, we want to build the quantum system, the parameterize, the ansatz. And three, we want to run the VQE hybrid loop and solve the problem. So first is first, we want to find the Hamiltonian operator. I won't go into the classical, this is all classical math, I won't go into it. But basically, the min vertex cover can be formalized as this expression, as this quadratic expression. We're basically trying to minimize the set of vertices and make sure that at least one of the vertices from each edge is covered in the graph. And this can be mathematically transformed with a simple operation, which we won't go into, and we can obtain our Hamiltonian operator. So that's one. Now we want to build the quantum circuit. So actually the quantum circuit itself is technically super simple. First of all, the number of qubits that we're going to use completely correlates to the number of nodes in the network. So in our example, we have 12 nodes in the network, so we'll use 12 qubits. Then we prepare the system in an equal superposition, meaning that if we measure that circuit at that point of time, we'll have an equal probability to get any of the solutions within the search space. Now, all we need to do is apply alternating cost and mixer unitary operators. So the unitary operator represents the time evolution of a system with the cost Hamiltonian, sorry, the cost unitary operator represents the time evolution of a quantum system with a cost Hamiltonian. And the mixer unitary operator actually represents the time evolution of a quantum system with some other Hamiltonian. Let's call it the mixer Hamiltonian. And by actually putting them one after the other, or applying them one after the other, we're approximating discrete time evolution steps of a quantum system with a combined Hamiltonian, both cost and mixer. And given the right parameters and inspired by the adiabatic evolution theorem that was discussed before, actually we can transform the system from the mixer Hamiltonian state to the cost Hamiltonian state. And since we started with an equal superposition, which is the ground state of the mixer Hamiltonian, we should end up at the ground state, or the minimum energy state of the cost Hamiltonian. So that's pretty cool. And now we have a quantum system that actually makes sense, and we can use it. If we want to look under the hood of the unitary operator, that's pretty easy as well. And here we have a 3-qubit example. So if we exponentiate the cost Hamiltonian, we end up with 2 terms. One is the single qubit term, and the other is the 2 qubits term. And those are simply encoded into our quantum circuit. So for every node in the circuit, or every vertex actually in the graph, we're applying a single qubit RZ operator. That's pretty easy. And for every 2 qubits, which represent 2 nodes in the graph which have an edge between them, we apply 2 qubits RZZ operator, and that's it. The mixer Hamiltonian is even simpler. It's just a bunch of Pauli X operators, and if we exponentiate them, we just get Rx operators encoded on each of the vertices. So now let's solve our example, and we're going to do that using Classiq. So we're going to define the model, synthesize a quantum circuit, parameterize quantum circuit, and actually execute it. So Classiq actually has its own high-level descriptive language called QMod. It's pretty cool. So on the right, you can see how the QoA is simply implemented with the native language. You can see the cost operator, the mixer operator, and actually what's nice about it is that it lets you encode the classical model into the quantum model itself. Once we have the model ready, we can synthesize it and, and view the quantum circuit. This is an interactive view that you can see on the Classiq platform, but it doesn't really matter. This is the circuit as we discussed. You can see the layers. This is the mixer layer, and then a bunch of alternating cost and unitary operators as we discussed. And if we freeze and look inside the unitary operator, the cost operator, we'll see exactly what we discussed. So for each qubits in our toy model or our graph, for example, between nodes 8 and 10, there's the RZZ operator, and this is how it's implemented. And nodes 5 and 11 have the RZZ operator within them. And now we're ready to actually execute it. So we can either execute it through code or through the web application. And we can see how the energy, the classical optimizer converges the energy with each iteration, and we end up with the minimum vertex cover that we were aiming for. So, I don't know why the presentation was so obscure, awkward, so I'm sorry, but let's conclude. So three things. We successfully solved our toy 12-qubit system. It's true, QoA has a lot of caveats, but still, you can run it on today's NISQ noisy computers. And given some improvements in quantum computer hardware, it shows real promise. So this is one takeaway. The second, we demonstrated the simplest example of graph optimization. There are much more complex examples that we can use using attack scenarios, prioritizing events, saving data within the network, and so on and so on. And we're actually working on some of those. So that's pretty cool. And thirdly, there are a bunch of other algorithms out there, machine learning, search algorithms, and so on, that can also be applied to cybersecurity. I'll just leave us with a general sentence that every threat carries an opportunity, and we're hoping for peaceful times ahead. Thank you. Sorry?
How do you calculate the gradients of your parameters in the parameter sheet?
So you can use any classical optimizer. You can use gradient descent or some others. So you can choose any, and that's a great question, actually. So you can play with the parameters and the optimizer, and that actually changes or affects the results, if that's what you asked, right?
Can actually calculate the gradients?
Yeah. This is what the classical optimizer does. This is how it knows to update or feedback the parameters back to the quantum circuit. It's unclear and needs to be tested when the quantum computers become when they actually work. But it shows some promise of beating the classical computer even with the approximation algorithms, but it's not mathematically proven.
Questions? Ariel, thank you very much.
Thank you.
Appreciate it.